Okay, now I'm going to make your head explode. So pause and copy. Um, Pause and copy. Okay, I am trying to convince you here that in the vector space definition, there is a lot of flexibility. Okay, we have an operation called addition. What do we mean by addition? We don't mean anything except what is written here. We have an operation called multiplication by scalars. What do we mean? Well, you may have some ideas in your head about what that means. Try to forget them and only think about what's written here. Okay, so addition can be anything as long as it passes these tests. And multiplication by scalars, likewise, can be anything as long as it passes these tests. So we are going to define, just for fun, on this set here, we're going to define a strange addition and a strange multiplication by scalars. Okay, to help you out here, maybe you want to put a circle, change the plus, so make it a circle around the plus just to, um, it may help, just so you don't confuse it with the kind of plus sign that you're used to. And then the dot, likewise, you can put a little circle around that just to emphasize that we're doing something different here. Okay, so addition is defined to be multiplication. And scalar multiplication is defined to be exponentiation. Okay, so this is a very strange set of definitions, but you can prove that this is indeed a vector space. Um, so why don't I do some of these for you? How about I do 2 and what's interesting? 2 and 7. And then I'll leave the rest to you to do if you want to. So we'll say this is an exercise. Okay, here I'm just telling you what's what here. This is what scalar multiplication is. I'm just saying the first number is the scalar, and the second number is the vector. Okay, so what did I say? I'm going to prove 2 and 7? Yeah, 2 and 7. So 2. So I need to show that u plus v is always equal to v plus u. And I'll put my circles here to indicate I'm doing something different. Fix my v. Okay, so let's start with the left-hand side. What is u plus v? Well, that is equal to the product, right? Now, this product here is the product in the real numbers. So it's the usual product in the real numbers. Okay, for that reason, we can rearrange v and u. And then we use our definition again, but backwards, to get v plus u. Okay, so each equal sign can be further justified. So this equal sign is by definition of our addition, and likewise this one is by definition of our addition, and right here is just a property of multiplication of real numbers. So that is all we need to show. Seven. So what was 7 again? 7 was one of the axioms governing the interaction between scalar multiplication and the addition. So C. C U plus V. So I need a dot. Use my new notation. My dot looks like that, and my plus has a circle. So I want to prove this distribution property. So start with the left-hand side. I get C dot U plus V is, what is that? U plus V. What is that? Well, I get C dot, this is UV by definition. And then I get, by using the definition of scalar multiplication, you get the C as the exponent. Excuse me. And now we are entirely in the realm of just real numbers. So exponentiation, it works the way it normally does, right? So now I'm just going to pause and remember what I'm trying to do. I'm trying to arrive here. Okay, so how can I do that? Well, I'm there, aren't I? So maybe just use brackets to emphasize. So this is C. So let me just finish this and then I'll come back and justify every equal sign. What's the last thing? Okay, this product right here is the product of real numbers. So that becomes my plus sign, right? Oddly enough. There we go. And that's what I wanted to get up here. Okay, how can I justify each step? So I'm using the definition here. Where else am I using it? I'm also using it here and here. Okay, what I mean is definition of my vector space. Now, what else? Oh, also this equal sign. And the remaining equal signs, these are just properties of real numbers. Okay, so I proved 2 and 7 for you. If you want, you can go and think about the remaining axioms. Okay, it's fun to think about what the zero vector is going to be in this case. And cancellations, what do cancellations look like? Well, I'll leave that to you and let me know if you want any help.